Alright, so we can start from where we left last time. Can anyone remind me what we talked about last time, please? Yes, last time we talked a little bit more about springs, and we started by looking at springs in series and parallel. In particular, we said that when we have systems of springs, and I'm going to share the screen as well so everybody can see it. So in particular, when we have systems of springs, they can be either in series or in parallel, and we can simplify our system by replacing these springs in series or in parallel with equivalent springs. So we went through a couple of derivations for the first case and second case. So in the first case, when we have spring in series, we know that they are subjected to the same force, and by knowing that they are subjected to the same force, we can calculate the first displacement, the second displacement. The total displacement will be given by the summation of these two, so we can plug these two quantities here. Basically, what do? We replace our springs with a block that has an equivalent stiffness, so it means that we can write this equation for the entire system. So the weight, in this case was the weight of the mass, is equal to K equivalent multiplied by the total displacement. And then basically we can rearrange this equation. We found the total displacement from here, we can plug here, and then we obtain the K equivalent for two springs in series. Of course, we can extend this one to a generic number of springs, and then we obtain K equivalent 1 over summation between 1 and n of 1 over Ki. So this is valid for any number of springs in series. We can do the same thing for springs in parallel. In this case, we know that the springs in parallel are subjected to the same displacement. In this case, when one spring is stretched, the other one is compressed, and vice versa. But the amount of displacement is the same for both. So knowing this, we can simply determine, we know that the force, of course, of the two must balance the weight of the mass in this case. Also, we can write the equation for each spring. We know that the total force must be equal to the weight. So we know that the displacement is the same, so instead of using delta 1 and delta 2, we can simply use delta. And then we can find the new expression for K equivalent when we have any number of springs in parallel. And then we went through a problem. So in this case we have two springs in parallel, and then we have two springs in series. These two springs in series are in parallel with another one, and then we went through simplifying the system by replacing two or more springs with the equivalent spring, and then eventually we can find the natural frequency of the whole system by considering one single spring that is equivalent to the 5 springs together. Then in the second part we talked about beams, pretty much, because we know that we can model materials as springs, because if we recall the stress-strain diagram, we know there is a portion of the stress-strain diagram that is linear. That portion, so in that portion, materials behave exactly like spring, because there is a linear relationship between, in this case, stress and strain, which is the same linear relationship between force and displacement. So by doing this, we can actually introduce new quantities that allow us to model beams as springs. Depending on the type of motion that we have in our beam, this expression can change. So if we have a longitudinal motion, the equivalent stiffness of the beam will be EA over L. E is the elastic modulus, A is the cross-sectional area of the beam, and L is the length of the beam. If we have a twisting motion or torsional motion, same thing, we have the equivalent stiffness of the beam is given by Gj over L, where G is the shear modulus of elasticity of the material, J is the polar moment of inertia, and L is the length of the beam. Third case, we can have a transverse motion. Transverse motion means the motion is perpendicular to the axis of the beam. Even in this case, we have the equivalent stiffness, which is 3EI over L cube. E, same thing, is the elastic modulus of the material, I is the moment of inertia, and L is the length of the beam. We also introduced another equation that we can use to actually to design an actual spring. So this equation basically tells us how to calculate the stiffness of the spring by knowing the material of the spring and the geometry of the spring. So here we have D, which is the diameter of the wire of the spring, N is the number of turns, and then R is the radius of the spring. We also started to look at a problem. Is there any question about all these equations that we saw last time? Alright, if there are no questions, we can quickly look at the problem that we started last time. So here we have to calculate the variation of the natural frequency of a wing of an airplane with a fuel tank at the tip of the wing, if the fuel tank is either full or empty. So the mass of the empty fuel tank is 10 kilograms and the mass of the full fuel tank is 1000 kilograms. The moment of inertia of the cross-section of the wing is 5.2 times 10 to the power negative 5 meter to the power 4, and the modulus of elasticity of the material is 6.9 times 10 to the power of 9 Newton per meter squared. We also know the length of the wing, which is 2 meters. So today is so how should we approach this problem? Any idea? Any suggestion? Did we solve the problem? I think we just talked about it. Did we go through the actual calculations? Yes, exactly, that's true. So basically, to approach this problem, we consider the transverse motion of the this situation of transverse motion. So we can easily model our our wing as a cantilever beam, where we have the tank, and then of course we have this transverse motion. The only thing that we have to do is to recall the equation that we used to find the natural frequency. So we have omega n for the full tank is going to be equal to the square root of k over, we can call mf, which is the mass of the full tank. In order to determine the k, we use the expression that we have here, because we are talking about transverse motion. So we'll have 3EI over L cube multiplied by the mass of the full tank, and then square root. In the second case, for the empty tank, we have same thing. You can call this ME. Of course, the stiffness doesn't change. That doesn't depend on the mass. So we still have 3EI over L cube. But of course, what changes will be the mass that we use in this case. So we have ME. When we plug the numbers, we obtain that with the full tank, the frequency is 1.8 Hertz, and then with the empty tank the frequency is 18.5 Hertz. So this is how the natural frequency changes with the mass of the tank. Make sense? This was pretty straightforward. We can quickly look actually at another problem. This problem here is actually very similar, so we can just read it and talk a couple of minutes about it, and then we can see another when we go through a couple of calculations. So in this case we have a person standing on a diving board, can be modeled as a cantilever beam with a concentrated transverse load at the tip in this case. If the mass of the diver is 100 kilograms and the length of the board is 1 meter, determine the value of the flexural rigidity of the board if the diver wants to oscillate at 3 Hertz. So please spend like 2 minutes to think about this problem. Exactly. In this case, we need to just use the exact same equation that we used before, because it's the same type of motion. It's also a transverse motion, so we can model our diving board. The person would be here, to be the diver, and we know the mass. What we have to find is the value of the flexural rigidity. So the flexural rigidity is the product between Young's modulus and moment of inertia. Just as a reminder, EI is the flexural. So in order to have two beams with the same flexural rigidity, they must be made out of the same material and they must have the exact same cross-section. This is the only way to have the same flexural rigidity. Now, in our case, for this problem, again, this is what we have to find. So we start from the definition of the natural frequency. So we already know that it's the square root of k over m. We know that for the transverse motion, the value of k is 3 EI over L cubed. So we have 3 EI. So we can plug this quantity here, and then, as we just said, we can simply work backward. So basically, this term here, EI, is what we need to obtain. So when we go through a couple of steps, what we obtain is that EI is equal to omega n squared times m times L cubed divided by 3. Make sure that you are consistent with the units. When we use this equation here, omega n is in radians per second. So the value of the frequency that we had from the statement is in Hertz. So make sure that you plug the correct value of omega n here, which will be the value of the frequency in Hertz multiplied by 2 pi. Basically. So we will have 6 pi squared times 100, which is m, times L cubed, it was 1 meter, so 1 cubed divided by this constant 3. We plug all the numbers, what we obtain is 11843.5. The units of the flexural rigidity are newtons per meter square. So Newton multiplied by meter square, because it's the product between E and I. E is given in Newton per meter square. I is given in meters to the power of 4. So we multiply these two quantities, what we obtain is Newton multiplied by meter square. Make sense? Any question? Yes. So this is meter to the power of 4. So if you multiply meter to the power of 4 by Newton over meter squared, you obtain newtons per times meter squared. Alright, I think we can go over another simple problem now. Here we have another problem. So we have a model helicopter landing gear consists of a metal frame that can be approximated to a beam with length equal to 0.4 meters. The weight of the helicopter is 100 kilograms and it is parallel to the axis of the beam. So the weight is parallel to the axis of the beam. The material of the beam is steel, and what we have to do this time is to calculate the cross-section of the landing gear in order to have a natural frequency of 500 Hz. So please spend a couple of minutes on this, and then we can try to solve it. Exactly. So the process is actually very similar to the one that we saw before. So in this case we have to pay attention because the difference with respect to what we were seeing before is that now we are looking at longitudinal motion rather than transverse motion. So according to the description that we have from the statement here of the problem, we can model our landing gear. So let's say if this is the wheel, this is the ground, this is our landing gear, and this would represent the mass of the helicopter. So the mass of the helicopter would move in this direction, which means that for our beam it is seen as a longitudinal motion. Okay? Since this is seen as a longitudinal motion, of course we have to use the K equivalent, the stiffness of the beam when it is subjected to a longitudinal motion. So the process, once we know this, the process is exactly the same. So we work with the natural frequency as the ratio between K and M over square root. In this case, K is equal to EA over L. When we plug this quantity here and then when rearrange in order to obtain A, because in this case we are asked to find the cross-sectional area, we can obtain the value of A. So we have A equal to omega n squared times L times M divided by the Young's modulus. So in the statement the Young's modulus actually was not given, but we know the material. We know that the Young's modulus depends on the material that we have. We know that we are working with steel in this case. The Young's modulus of steel is approximately 200 gigapascal, so it's 2 times 10 to the power of 11. So when we plug all the numbers here, what we obtain is 1.97 times 10 to the power of negative 3 meters squared. Also, please pay attention to what you put here, because this is the natural frequency expressed in radians per second. Here we have the natural frequency expressed in hertz, which means that we have to multiply this quantity by 2 pi in order to obtain omega n. So the numbers that we will put here are 2 pi times 500 squared, L is given already in meters, so times 0.4. The mass is already given in kilograms, so times 100. And then we divide by the Young's modulus. Again, for steel is 200 gigapascal, which means 2 times 10 to the power of 11, or 200 times 10 to the power of 9, same thing. And then when we do this calculation, this is what we should obtain for the cross-sectional area of the beam. Make sense? Any question? So please keep in mind that, of course, when we go through all this modeling of springs for longitudinal motion, twisting motion, transverse motion, of course we kind of isolate them, which means in this case we consider only longitudinal motion, in this case only twisting motion, in this case only transverse motion. Of course, in the real world, structures that are subjected to vibration are typically subjected to combinations of these motions. So it means that when we look at a real case of an actual structure, we will need to combine the contribution of the longitudinal motion together with transverse motion, together with twisting motion, again depending on what type of actual situation we have. Make sense? Any question before we move to the next topic?